All right, this is section 12.3. Today we're going to be talking about drawing angles in standard form, talking about reference angles, degrees, radians, coterminal angles, and trig functions. So we have a lot to cover, so let's go ahead and get started. So we're talking about drawing angles in standard form. So this is going to be talking about if I am drawing an angle in an XY coordinate grid like so. Then we would wind up getting stuff like this. Now, there are some things that we need to note. Whenever I do start drawing, we have the two sides of the angle. We call the initial side and the terminal side. Now, the initial side is always going to be the side of the angle that is starting on your x-axis. So, for example, right here, if I look at these angles right here. So, my initial side is always going to be the side that's flush or it is overlapping with your x-axis. Whenever you draw an angle, you always start on the x-axis. Your terminal side will be your other ray that helps to create your angle, and it can go literally in any direction it wants to. So for this one, it looks like it is coming out here, pointing kind of up and to the left. And so therefore the amount of the angle is being created like here, and it's being represented by theta. But if we were to maybe give it an angle measure, sure, we could maybe say this is around 135 degrees, something like that. Now, whenever we draw angles, we are always going to draw angles in a counterclockwise direction. So like the one that we have drawn here, we started at my red x-axis and we drew to the left in a counterclockwise fashion. And this would give me a positive angle measure. Now, I can go in a clockwise fashion, but when I do that, I'll create a negative angle. So, for example, if I started once again at the red x-axis, and let's say my terminal side wound up being down here, so that, and I would show whenever I draw that my green arrow is pointing down to my terminal side. My arrow for my angle always points to my terminal side. And we could say maybe this is about negative 50 degrees, just to throw a number out there. But that's the idea, is that if I'm drawing a positive angle, I need to draw counterclockwise from the x-axis. And if I'm going for a negative angle, drawing clockwise. And then, as always, a full revolution would be 360 degrees. So let's practice a few of these real quick. Now, whenever I'm drawing these things, it's important that we can go ahead and split this thing up so I know when I'm supposed to be crossing the line, when I'm not supposed to be. So we always start at the x-axis. Like usual, this would be my 0 degrees. Now, if I go all the way up to the top of the y-axis, then I'm a quarter of the way there. And a quarter of the way around the whole thing would be a quarter of 360, would be 90. If I go to another, so the other end of the x-axis, now I'm halfway of 360, so 180. Go all the way down to the bottom of the y-axis, now I'm at 270. And then back all the way around, I'd be back at 360, which is in the same spot as 0. So if I'm graphing a 75-degree angle, well, that's positive, so I know I need to go counterclockwise. And so we're just going to kind of eyeball. It ain't got to be necessarily perfect, but I know that 75 is not bigger than 90, so I should not cross the y-axis, but I should get pretty close to it. So if I'm drawing a 75-degree angle, we could say something maybe about like this. That would be a decent 75-degree angle. Now, what if we're going the other way? If we're going negative, well, again, feel free to put some little bookmarks for you so you know where you're passing. So if I'm going for a negative angle, I'm going to draw clockwise. So again, I'll always start here. That's my 0. Now, last time we went counterclockwise and hit positive 90 up at the top of the y-axis. But if I go clockwise, then I can have negative 90 at the bottom of the y-axis. Go another bit. Now I'm at negative 180. Up at the top of the y, now I'm at negative 270. And then finish it all the way out, I could have negative 360. So whenever I draw a negative 160-degree angle, well, I know that negative 160 is, well, technically it's not bigger. Technically it is bigger, but not smaller. I'm not going to go past negative 180, but I am going to get awfully close. So we could say maybe about like this. And since I'm going for a negative angle, not a positive, I'm going to draw clockwise like so. And this would be my negative 160. As always, we would start here at my initial side. Now for a 430, well, 430, that's going to be bigger than a full revolution. So again, we have our 0, 90, 180, 270, and then back to 360. So in cases where I'm going bigger than a full revolution, again, positive, so I'll go counterclockwise. I'm just going to basically just do like a little loop, like so, like that. So that's going to be my 360. And yes, I did purposely make sure that it didn't connect together because I'm going to keep going with it a little bit further. So 430 is going to be 360 plus a little bit extra. The little bit extra, I can just subtract. And I know I need to go 70 degrees extra from a full revolution. Well, we kind of eyeballed the 75 over here, so we'll get pretty close to that one as well. So a 70 degree, maybe about like this. And so we finish it out like so. All right, so that's graphing these things in a standard form. Now let's talk about different ways that we can calculate their measures, because we're used to only doing it in degrees, but there is another way that we can measure angles, and it is what we would call a radian. So a radian in and of itself is going to be a unit of angle measure that is based on arc length. So arc length, coming from the arcs, are the edges of the circle, portions of it, and arc length would be basically a piece of a circumference of a circle. Okay, so think of it as like a side length in a square. It's just going to be a piece of the circumference. Now, whenever we define a radian, it is talking about a circle with a radius of 1s. And just kind of our two main points we use as conversion points is that 360 degrees is equal to 2 pi radians. Okay, so you're going to see a whole lot that pi usually pops up whenever we are talking about radians. So 360 degrees is 2 pi radians, and so therefore we could half both of those to make another point. 180 degrees would be classified as pi radians. And we can convert between degrees and radians by doing the following. So if I am trying to go from degrees to radians, so like on number 4, then basically the quickest thing that I'm going to do is I'm technically multiplying by pi over 180. That is technically what I'm doing. But I also just like to think of it as divide by 180 and put a pi up top. That's 9 times out of 10, that's going to get you what you need. But multiplying by pi over 180. So when I reduce, 30 over 180 will become 1 over 6. And I don't have to have that 1 there because I have a pi up there instead. So 30 degrees is the same as pi over 6 radians. And whenever we would say this, we would say it exactly like that. We would say this as pi over 6 radians. But I don't have a symbol like with a degree. We have the little circle. I don't have a symbol for radians. This would just be how we would write it. We would just write pi over 6. And that would be it. So for 150, same deal. So we're going to multiply by pi over 180. We would reduce 150 over 180, and we would make this into 5 pi over 6 radians. And if it's a negative degree measure, again, it does not change it. We would multiply by pi over 180. Negative 220 divided by 180 reduced is negative 11 over 9. And of course, we stick the pi on there. Negative 11 pi over 9 radians. Now, if we're going the other way, then you're going to flip it. Instead of multiplying by pi over 180, if you're going from radians to degrees, then now you'll multiply by 180 over pi. And again, 9 times out of 10, what this is basically going to be doing is the pi's, 9 times out of 10 should cancel if you have 1 in top and 1 in bottom. And then for your numbers, you're basically multiplying by 180. So 4/3 times 180, or 4 times 180 divided by 3 will give us 240 degrees. Number 8, negative 5 pi over 36 radians multiplied by 180 over pi. So again, the pi's will cancel. And even if you type this into your calculator exactly like that, the pi's should still cancel. So negative 536 times 180 should give us negative 25 degrees. And then 7 pi over 4 we're going from radians to degrees, so we're going to multiply by 180 over pi. The pi's will cancel, and this will give me 315 degrees. All right, so now let's keep going with it. So this whole idea of converting between degrees and radians, because now we're going to start seeing angles in both forms. So let's talk about coterminal angles. Coterminal angles are going to be angles that have the same terminal side. So again, we talked about the initial side is always the same for every angle. It's always going to be basically the right side of the x-axis. But if we have two angles that also share the same terminal side, they are called coterminal angles. But just because they share the same initial and terminal side does not mean that these will be two equal angles. Not necessarily. But if we were to draw them, they would both begin and end in the same spot. So, for example, if we're looking at this one right here, the example they gave us is if you had a 90-degree angle or a pi over 2 radian angle, then it would be drawn like so. You would start on the right side of the x-axis, you would go counterclockwise a quarter turn, and end on the up part of the y-axis. But if you were also asked to draw a negative 270 degree or a negative 3 pi over 2 radian angle, then you would still start at the x-axis, and you would go clockwise a 3/4 turn, and end here as well. So 90 degrees and negative 270 degrees. They both start and stop in the same spot, but they were different paths to get there. That's what it means to be coterminal. So let's look at a few of these. The directions ask us to give two coterminal angles for each one. We're to give one positive and one negative. Well, the quickest way to do this is going to be if we're having to think of this as they have to start and stop in the same place, we're thinking about going basically a full 360 around from where they would have started. So, for example, if I have a 65-degree angle, okay, if I was just to graph this real quick, you don't necessarily have to graph it, but if we were to graph real quick, let's say eyeballing it maybe about like this. This would be a 65-degree angle. Then we would need to find two other angles that would start and stop in the same place. Well, one way we could do this is if I do a full 360 and then go 65 more. So what I did is I said 65 plus 360, and that would give me 425 degrees. Well, that would be another angle that would start and stop in the same place as the original 65. So I can think of this as I'm just adding a full 360 to my original angle to get a coterminal angle. Now, I could also do that process in reverse as well. So if I instead went clockwise and did a full rotation, then I would wind up getting the same thing as well. So if I go 65 minus 360, and that's going to give me negative 295. Now notice, I don't have to go all the way around for this one, but if I went that way, then yes, negative 295 would start and stop in the same place. So 425, negative 295, these are two coterminal angles of 65. Now, there are an infinite amount, but I'm only asking for two. All right, so what about for number 11? Well, a 540-degree angle, we don't necessarily have to draw that one now that we know the trick. Now, I can get another positive one, obviously, if I just add 360. And so I would get 900 degrees. So that is one coterminal to 540. But now if I want to get a negative one as well, because it's not asking me just to add one and subtract one, it wants two coterminal angles, one positive and one negative. Well, if I go 540 minus 360, I'm at 180. And that is still positive, so I'd need to do it one more time. So if I subtract 360 twice, then I will get negative 180. And so that would be another coterminal angle, 900 and negative 180. Now we can still do this process also with radians as well. We just got to think about what we are now adding and subtracting instead. So 13 pi over 18 radians. Now, the last ones I was adding and subtracting 360 degrees to get my coterminals. Well, keep in mind that 360 degrees is equal to 2 pi radians. So instead, if my angle is in radians, I'm not going to add 360 to it. I am going to add or subtract 2 pi radians. Now again, sometimes this will work out very nicely, sometimes it won't. You just have to pay attention to what it's wanting. It's wanting to have one positive and one negative, so we may have to add 2 pi twice, we may have to subtract 2 pi. It doesn't really matter. But with this one, so I can get, if I add 2 pi, so let me get rid of that minus sign. So let's say if we do 13 pi over 18 plus 2 pi and reduce it, we will get 49 pi over 18 radians, and that is one coterminal angle. And then if I do the other way, 13 pi over 18 minus 2 pi. And again, feel free to do this in your calculator. You don't have to put the pi in there. You can just do 13 over 18 minus 2. And this should give you negative 23 pi over 18. And these would be two coterminal angles. Now, for some of you, it may be a little bit easier, just because radians are still new to you, to turn that into a degree and then work with it. And that's completely fine. If you want to turn 13 pi over 18 into whatever it would be in decimal form or in degree form, you're more than welcome to. Just make sure that your final answer matches the original question. So if you start with radians, your final answers need to be in radians. All right, number 13, we have 14 pi over 9. So I can find a coterminal first by adding a full revolution. So by adding 2 pi, and I'll get 32 pi over 9. And then if I go the other way with it, 14 pi over 9 minus 2 pi, then I can get negative 4 pi over 9. And again, one positive and one negative. But again, you do have infinite amount of reference angles. Or coterminal, excuse me. I just mentioned coterminal, but now let's talk about actual reference angles. So now, reference angles are slightly different from coterminal angles. The reference angle is going to be a positive acute angle that basically takes you back to your x-axis. So with every single one of these, we're basically asking ourselves, no matter if we are above the x-axis or if we are below the x-axis, we're trying to figure out how far away from the x-axis are we. So, for example, if I start by graphing a 225 degree angle, so remember we have 0 degrees here, 90, 180, 270, and then full 360. So if I'm graphing a 225, positive 225, I'm going to go quarter turn, half turn, and then about halfway through my third turn. So that would be about a 225 degree angle. So now the reference angle, where it's going to come into play, my reference angle is the amount that my terminal side, which is where we stopped, is away from the x-axis. So for example, when I was drawing this thing, I did my quarter turn and then a half turn, and then I did not complete another quarter turn. Instead, I went from 180 and I went an extra little bit to get to 225. Well, how much was that extra? That extra, and that's what we're measuring as our reference angle, is going to be an extra 45 degrees. Because I went from 180, and to go from 180 to 225, I had to go an extra 45 degrees. So my reference angle for a 225 is 45. And it doesn't matter that I went below the x-axis. Reference angles, we're always just going to consider to be positive. All right, so even if I have with number 15, a negative 310. So again, make your little markers. So we have negative 90, negative 180, negative 270, and negative 360. Well, if I'm going negative, I know that I need to go clockwise. So quarter turn, half turn, 3/4 turn, and go a little bit more like so. All right, so here's our negative 310 degree angle. So the question is, if we were to keep going a little bit further, because we're trying to get back to the x-axis in the shortest way possible, how much farther would we have to go? Well, we did our 3/4 turn, and then we went another negative 40 degrees. Now, last time that wound up being our answer was that we went a 1/4 turn, a 1/2 turn, and then an extra 45. So 45 wound up being our reference. But with this one, the extra little bit that I went was an extra, let's just say it's negative 40 technically, but I'm going to say we went an extra 40 past the 3/4 turn. But we're trying to get back to the x-axis, not the y-axis. So I am 40 degrees away from the y-axis, but my reference angle is how far away I am to my x-axis. And that angle is 50 degrees. So my reference angle here is telling me how far away I am getting back to the x-axis. So this one would have to be a 50 degree angle. All right, number 16, we're looking at 2 pi over 3 radians. Now, again, for some of you, this might be a little bit easier to visualize it in degrees. So if you convert 2 pi over 3 radians, this would be the same as 120 degrees. So if I was to draw this angle, we get something about like this. That's about a 120 degree angle. So again, I'm well aware that I am closer to my y-axis. I'm 30 degrees away from my y-axis, but a reference angle does not matter. It does not care about the y-axis. It cares about how far it is from the x-axis. So to get back to the x-axis, the quickest way is to go that way, going counterclockwise a little more. And in this case, we are 60 degrees away. So that would be it in degrees, but let's try to stay consistent. If we started with radians, we'll finish with radians. So 60 degrees or pi over 3 radians. All right, so now for this last little bit, let's revisit this trig stuff that we talked about on Monday, but this time using it in drawing angles in this little XY grid, okay? So we talked about Pythagorean theorem and all this yesterday. We had a squared plus b squared equals c squared. Well, now let's talk about it from a slightly different point of view. Let's talk about it from x squared plus y squared equals r squared. So if you were to take a point P with coordinates x, comma, y, and this point P is going to exist on the terminal side of your angle, so how they have it drawn here, well, then we would be able to create from the terminal side, the x-axis and the y-axis, we're able to create a right triangle with side lengths of x, y, and r. And so then we're able to then place theta inside of our triangle. We always want to place theta at the acute angle that is closest to the origin. So that's why I kind of rewrote theta to instead go where I want it to go, right there. And so then we just kind of revisit what sine, cosine, and tangent are. It's all depending on our theta, identifying our opposite, our adjacent, and our hypotenuse. So in this case, y being my opposite side, x being my adjacent, and r being my hypotenuse. So let's look at number 17 to finish this section of notes out. So we have point P is at the coordinates 5, -2, and it is a point on the terminal side of theta in standard form. Find the exact values of the following trigonometric functions. So let's just graph that point real quick. So 5, -2, we'll kind of eyeball it. Let's say 5 is maybe about like right there, down to -2. So we'll say maybe about right here. Here is my point P at 5, -2. This is on the terminal side of an angle that I was drawing. Okay? Well, we can create a right triangle out of this terminal side. So the point 5, -2 is going to help me figure out what my side lengths are. So if I was to go straight back up, this will tell me how far up or down for my y-axis I am. And this would technically be -2. Usually we think of the triangle having positive side lengths, but for right now, we're going to leave that -2 in there for right now. And then going across the top, we have a length of 5. And if we then want to figure out what my red line is, my hypotenuse, then we'll need Pythagorean theorem. So if we set up Pythagorean theorem, we can set it up as 5 squared plus negative 2 squared. Again, make sure you put your parentheses there, is equal to c squared. All right, so we get 25 plus 4 equals c squared. So this is going to give me, or I guess I need to use an r squared actually for this example. So we're going to get that r is equal to square root 29, which we cannot break that down anymore. So now, to figure out what all my values are going to be, my theta has got to go in the acute angle closest to your origin. So this will be my theta right here. So this tells me that negative 2 will be my opposite, 5 will be my adjacent, and root 29 will be my hypotenuse. So when we set all these things up, and this will be our last little bit, sine of theta, opposite over hypotenuse, will be negative 2 over square root 29, which we're going to simplify. We're going to rationalize the denominator and make this negative 2 root 29 over 29. And then when I do cosecant, it's reciprocal. I'm going to flip it. Now you can flip the new one, but it might be a little bit easier in this case just to flip the original, like so. And again, with the whole negative in a fraction thing, it doesn't really matter where you put it. It can go up top, on bottom, or in front. It does not really matter. All right, then we fill in the rest of them. So cosine, originally, we could say it was 5 over root 29. But we will rewrite this into 5 root 29 over 29. Secant, we can just flip the original, root 29 over 5. Again, you could work from 29 over 5 root 29, but it will wind up being just a lot more work than we necessarily needed. And then lastly, with tangent, we have negative 2 over 5, cotangent, negative 5 over 2.